All right, we are continuing in this very long section on limits. We've talked a lot about techniques for finding limits. Now we have two little topics towards the end where we modify ways in which we can use this idea of limit, right? Once you have this intuitive idea that a limit is describing what are we getting close to, we can fudge it a little bit to apply it to unusual situations, right? And one might be where we have a jump in a graph. You can see this picture below. I have this graph where it's going nice and smooth. Then here at x equals 2, just out of nowhere, it drops down. We call that a jump. A jump discontinuity is the very formal term, but jump is sufficient. And if we're careful, we can modify the way we talk about limits to talk about this. Right, so let's look at this function here. Let's call this y equals f of x. If you're taking notes on this, you really do want to have this picture. Right, so pause and draw a picture. This is a weird piecewise defined graph. We're not going to have a single formula for it, but it is a function. For every x, there is a unique y. You'll notice here this open circle means that that point is missing. F of 2 is up here. This is a missing point, but then all of these are there. So we know there's a jump at x equals 2. But how would we describe the behavior of the function near x equals 2? And it's a little bit tricky to talk about what's happening near x equals 2 because there are two different places on the graph. Right, let's really think about this. Right, here down on the number line, right, all of these little dots here correspond to values of x that are near 2. Well, where are the corresponding points on the graph? Some of them are over here. All of these points right here that I've marked in green are points on the graph where x is close to 2. And in fact, as x is getting closer and closer to 2, we see that those y values are approaching 1. Right? This point right here is at 2, 1. So on the one hand, we see a pattern that says as x is getting close to 2, y is getting close to 1, which would mean the limit is 1. But wait a second, if we look over here, if we look at the values slightly bigger than x equals 2, here's where they're located on the graph. As x goes closer and closer to 2, over there we're seeing y gets closer and closer to 0. So here my y values are headed towards 1. Here my y values are headed towards 0, but the x is the same. So what is our answer? If x is getting really close to 2, which y value are we getting close to? Is it 0? Is it 1? Is it halfway in between? Well, so here's what we would remind ourselves. When we talk about the limit of a function, we should be giving one specific value that is approached. Right? When I say the limit is 5, that means just without a doubt, near that certain x value, my y values are getting close to 5. And in this case, there's no number that has this. On the one hand, it's 1. On the other hand, it's 0. So we're really not seeing that we have one specific value that's approached. So the most general thing we could say here is that for this example, this limit as we approach x equals 2 doesn't exist. Right? There's no guarantee that this is always going to give us an answer. Sometimes there's not enough of a pattern. In this particular graph, if x is close to 2, I can't give you a single specific answer as to what y is close to. So we would just say that that general limit, the limit as x approaches 2 of f of x, does not exist. Right? Please do not write this with an equal sign. Don't say equals does not exist. Right? This by itself is basically a sentence. This limit does not exist. You don't need an equals. If equals makes it wrong. So the limit doesn't exist. And yet we feel like there are patterns. Maybe there's not one big pattern, but there's a little pattern over here that makes sense. And there's a little pattern over here that makes sense. So we can modify the language of limits to talk about those patterns individually. What we're noticing is if we approach x equals 2 from the left. So here's x equals 2. This is the region of the graph that is left of x equals 2. And if I am approaching x equals 2 from the left, I definitely have a pattern here, and y approaches 1 from the left. Just get in the habit of talking about the direction you're coming from. Even though you could say, oh, we're moving to the right, don't say to the right. Get in the habit of saying from the left. People always talk about where we're coming from. But then, of course, from the right, y approaches 0 from the right. If we pick the region of the graph to the right of x equals 2, and look at what this graph is doing to the right of x equals 2, as we come in from the right, those y values are headed down to 0. So here is how we would write this. I have this limit here and this limit here, and you'll notice there's this little extra symbol here. There's this little extra symbol here. This is not positive 2 and negative 2 because it's coming after the number. This, all by itself, is just our little signal that means from the left, because negative side of the number line is the same as the left side of the number line. And this means from the right. So that's kind of the trick. If we have a jump and there's no single limit, but we still want to talk about the pattern we see, if you have a pattern from the left, you write a little minus sign after the x value. If you have a pattern from the right, you write a little positive sign after the x value. So just a couple of notes and observations. Right? There's a superscript of negative or positive. These are not positive signs and negative signs. They're not coming before. Right? We were not saying negative 2. There's a big difference between 2 with a negative after it versus negative 2. Right? These are not the same thing. If the positive or negative comes after, it's specifying a direction. As I mentioned before, the minus goes with left because the negative side of the number line is on the left. The positive goes with the right because the positive side of the number line is on the right. As I mentioned, we always talk about the direction from which we're approaching. Always just talk about from the left, from the right. Don't talk about the direction you're moving, talk about the direction you're coming from. When we say these out loud, we just say the phrase from the left or from the right. So this one here, if I were saying this out loud, I would say the limit as x approaches 2 from the left of f of x is equal to 1. Again, the limit as x approaches 2 from the left of f of x is equal to 1. Over here, and I'll do it in a slightly different order, the limit of f of x as x approaches 2 from the right equals 0. Some people will say from the negative side or from the positive side. That's okay, right? But use the word from when you actually say it out loud. And just to be clear, the general limit without a direct direction exists only if the two individual one-sided limits agree with each other. Right, so just as an example, if I know that the limit as x approaches 3 of h of x is equal to 7, then what do I also know? Well, then I know if I'm approaching it from the positive side, I must get 7. And if I'm approaching it from the negative side, I must get 7. Here, if there's no direction specified, it means from either direction we get the same answer. As long as you're approaching 3, y is getting close to 7. Approaching from the positive side, well, that's 7. Approaching from the negative side, that's 7. Right? If we don't specify a direction, it means both directions give us the same thing. So now let's look at an example. Think about this function, g of x equals the absolute value of 2x divided by x. And don't just reach for a calculator or a computer, actually plug in values. Pick a bunch of positive numbers, plug them in and see what happens. Pick a bunch of negative numbers, plug them in and see what happens. You will definitely notice a pattern. So then, once you understand that function, I want you to evaluate these two one-sided limits. Hit pause and actually try to figure this out. Okay, so what does the graph of g look like? Hopefully you noticed, right, let's do this down here. Hopefully you noticed that g of any positive number, g of 7 would be the absolute value of 14 over 7, which is 14 over 7, which is 2. G of 3 would be the absolute value of 6 over 3, which would be 6 over 3, which would be 2. G of 1.8 would be the absolute value of 3.6 over 1.8, which is 3.6 over 1.8, which is 2. If x is positive, we always get an answer of 2. But if we plug in negatives, absolute value of negative 10 over negative 5 is 10 over negative 5, which is negative 2. Plug in a different number, negative 2. Right, so here's what the graph of g looks like. It's a very unusual graph. If I plug in any positive number, my answer is 2. So it's like they're all along a straight line like so, although it's undefined here. If I plug in any negative number, I get an answer of y equals negative 2. So they're all along this straight line. And the function is undefined at 0. Right? So very simple, boring horizontal line, and then a jump discontinuity to a different boring horizontal line. So what's the limit of this function as we approach from the negative side? If we're approaching x equals 0, where the jump is, from the negative side, well, my y values are all at negative 2. Negative 2, negative 2, negative 2, negative 2, negative 2, negative 2. What is that approaching? It's approaching negative 2, right? It has this super simple pattern of negative 2, negative 2, negative 2. So the pattern is, oh, negative 2, right? They're getting close to negative 2 because they literally are negative 2. But on the other side, it's 2. So occasionally we will see weird graphs with jumps. This one-sided versus these one-sided limits give us a tool for describing what we're seeing. Okay, I will pause again just to keep the individual videos short.